Okay, hello again. So my name is Paul. I'm one of the research fellows at QUT working with Kerry. I'm going to try to fit this all in 10 minutes, 9 minutes 58 seconds. It's about resilience. So this is about how we developed a statistical model to work with, this is in ecology, with ecosystems, to model ecosystem resilience so that the managers of these kind of systems will then have our tool to be able to investigate and predict what are the management levers they can pull to try to maximize the resilience of their ecosystem and to mitigate the risks of human development. And this involved a big group of really good people. I guess the concept we're dealing with here, that you have some sort of metric that you're interested in, like population of the ecosystem or some status. And that might have changes just due to the baseline, due to normal, seasonal variations. And then you have some stress. That stress that produces some sort of loss. And then after that stress is removed, there might be a slow recovery process back to the baseline population. But sometimes then the ecosystem collapses and then it goes to zero, or it never recovers back to its original point. It recovers to some other point. And so our study was on seagrass ecosystems. And the thing is, in ecology, that there's actually a lot of uncertainty. So this, if you have, let's say this is one seagrass meadow, you don't have just one nice uniform patch of grass, right? So you have some probability of maybe high, so here we're talking about shoot density, so the number of shoots of grass per meter squared. So you could have some probability or some distribution of high shoot density, moderate, low, or zero shoot density. And the thing is that this is changing over time, so that's what makes it challenging. That as you go over time, you can go to sometimes seasonally that you have times of zero, no grass at all. And so basically the challenge is we want to predict or estimate this population given the particular species, the location, the acclimations to that location, the environmental variables like light, as well as the biological variables. And so for us, the stress we're looking at is dredging. So you kind of have, what the baseline conditions are before, and then your period of dredging, and then we assume, you go back to baseline, and then do you have recovery in the 5 years. And the thing is that resilience is not static. It's not, okay, this seagrass meadow has this level of resilience, and that's it. No, that resilience changes over time. With season, they're vulnerable, more vulnerable or more stronger at different times. And so this is a nice big global study. We had this, I guess I don't have time to go through it, but basically, you have your main outcome variables, so your population, your shoot density, your biomass, and your aerial extent. And this is affected by factors relating to recovery, to resistance. So I think that resilience talk the other day, David was saying he called it the buffer, the ability to buffer the stress. Time is a factor, environment as well, and then some species-specific factors. So just for seagrass, the two main pathways or processes for recovery are by seed and by lateral growth. This is grass. And the main mechanism for resisting is the physiological status of the plant, which for grass is how much rhizome carbohydrates it has. I imagine that's quite different to humans. So what makes it interesting is you have these feedback loops. And so what our model is actually trying to capture the biological and environmental interaction and their processes over time. Just to illustrate, what does this look like? What does the model do? Okay, so here, remember we talked about wanting to predict the shoot density. So, it's about 0.5 chance of high shoot density, about 0.4 chance of moderate shoot density, and so on. And then this is just showing light. So yellow is very good light, probability of 1 above sufficient light, and red is very poor light, probability 0 of sufficient light. So it's basically showing that throughout a season, as you run the model, as you're going from summer into winter, the light decreases, and then your population decreases. It's worse during the middle, towards the mid-end of winter, but then as the light comes back, the population is slowly able to recover. So far, so good? Cool. But actually, it's not just about shear density and light. So there's a whole range of factors related to loss, the recovery, the physiological status of the plants. And here, we're just showing, instead of the whole distribution, just the mean. So that basically, as the light worsens, the physiological status of the plant goes down, which then results in loss. Loss then reduces the population. And then as we go into the growing months, into the spring, the status returns, the physiological status, which leads to recovery, and then recovery in population. And that's probably a nice, quick, and easy way of talking about that without going through these. And of course, with any model, it's very important to validate. So this model was interesting because it used a combination of expert knowledge and data. So we didn't have anywhere near enough data to cover the whole environmental and biological processes and all the different things you can measure. And I suppose that's true with athletes as well. You can't measure everything all the time. But even though it was a combination of expert knowledge and data, we were able to get very successful predictive accuracy. So mean squared error is on the order of 0.02 to 0.05, so we're predicting the probability here. So yeah, it was a nice big global study, and I guess the thing to talk about would be probably this thing. So what is this thing? So this is talking about the different types of stress. So dredging stress from 0 months of dredging, 1 month, 2 months, all the way out to 12 months of dredging. That's what we have in the columns. The rows are different sites. These are just 3 different species, Amphibolus, Halophila, and Zostra. Within each cell, we've got a pie. So it's like a clock. So 12 o'clock is December, 3 o'clock is March, 6 o'clock is June, 9 o'clock is September. And then each slice of the pie, that is our resilience score. So here we're showing recovery time. So yellow is very short recovery time, and dark red is 60 months recovery time. And on the outer edge, you see how there's a green ring here, and then this has got a red ring, but with bits of green. So that's showing the multi-criteria. So here we're showing recovery time, but there's also things like, do I have it? Oh yeah. The resistance, so how much loss this suffers immediately after the stress, and persistence, so what's the risk of dying. And so that's what we're showing here. So here we've, again, from 0 months all the way to 12 months of dredging, so greater and greater stress, different categories of species, time again, time of the year. And so this is the time of the year that you apply dredging. So what we're showing is that depending on what time of the year you apply dredging, you have a different resilience response. And so for some species, the resilience score, so dark green is you satisfy resistance, recovery, and persistence. Yellow score is you only satisfy recovery, and red score is you don't satisfy any resilience criteria at all. And so from some species, it's interesting because they are very resistant. So there's all green scores up to 3 months, but then they die. Some species, they're not resistant at all. Even with 2 months, they're already dropping to yellow scores. They can only recover. But then they can recover with greater stresses. And then this one is the most resilient one, so it's resistant up to about 2 months, and then it transforms to more recovery-based resilience, and it's able to sustain that for, in some cases, for greater stresses. So I guess what it's showing is that resilience is dynamic. It changes in space and time, and that space and time and the actual stress that you're applying and the nature of it. And then these windows of opportunity for managing, so the management levers that you could pull to try to maximize the resilience, to mitigate the risk of loss, can be discovered, I guess, if you're able to develop a whole systems model that captures all these different interactions. And that they can be very useful because these timing, these ecological windows, can enable up to a 4-fold reduction in recovery time and 35% reduction in extinction risk. And I believe that's it. Oh, so this paper will be coming out on this soon, hopefully. So that's it. And, yeah.
How does this relate to sport?
Good question. I guess it relates to resilience in terms of how it might be applied to the human side of things. In terms of resistance to stress. So the stress could be training, stress could be competition. This is as far as I understand it, by the way, guys. In the recovery aspects, maybe not through reproduction per se, but through the physiological processes of the body to recover.
Say we're going to apply or try to go that direction with injury and recovery from injury, as an example. How much data would we need? How many different athletes would we have to look across, and to what extent? And how many variables would we need? So, because we potentially have that data, but I'm just like I'm trying to get a feel for how much of that data. Like, do we need 500 people and with 500 injury events, or do we need thousands? Or
I guess it depends really on the specific context, right? Are you looking at performance? If it's injuries, and let's say injuries are a rare event, then, well, how many? The way we approached it here, we looked at what are the processes, and so that means the biological processes and the interaction with maybe stress, training stress, for example. And then the recovery processes, okay, how many hours? And there might be a lot of medical data about that and expert knowledge about that already. To then start to go into, well, how many samples you need, I don't think that's a question we can answer straight away. I mean, we had 28 global sites, right, which is a lot less than 500 athletes.
okay.
But then I imagine the processes going on in the human body are probably quite complex. So, but you might be able to distill down what are the key processes as experts that are relevant to performance, or the key processes that are relevant to injury, which may be, and to specific injuries, not just any injury. Let's say you're interested in shoulder injuries for swimming or something. And then so there'll be more specific, more focused data or questions to ask about that.
Where we didn't have data, we used expert information.
Yeah.
You can even do a sort of a first pass of this with a small amount of data and a lot of guesses. to get the ballpark.
Yeah, maybe we, so
Then work out where the gaps
a
are.
lot of our data sets are missing bits and pieces of information, so it wouldn't necessarily be unrealistic to fudge or fill that in based on.
Yeah, that's right.
Yeah.
Well, the nice thing about this is that a lot of it is actually aggregated data at the end of it, so you're looking at like just probability of putting a barbell below the threshold or something like that. So you don't actually, like, you can deal more easily with non-complete data.
Okay.
Yeah.
So Paul and I have had a couple of chats about using the AMS data for that and seeing how we can make it specific to sport and start using that sort of stuff. But even with the injuries, if we don't have enough data for injuries, there's still a lot of information about that. And the AOS is going to have a heap of stuff on injury risk relative to TSB. So I mean, we can just use that framework. We don't need to reinvent the wheel, and then we can, once we have the framework there, and once it's just running in the background with the AMS, the more data that we collect, the more accurate it becomes for our particular instance. So we might have a different injury rate to the AIS, for example, but that'll only become apparent once we've got enough data to be able to test it. So in the meantime, it's probably a good estimation to be able to use that sort of data. So this is why we had, at least the sports science group would have seen, we sent out an email about the consensual model of an athlete thing that I'm trying to put together. So I'm trying to put together just those, the same as what Paul had up there for an athlete, so all the different aspects and what would affect performance in the end. So I think instead of looking at injury as our output variable, what we really should be looking at is performance as our output variable, and injury and illness are mitigating variables on that. So they're negatives that we want to minimise. But the only reason we want to minimise them is because they affect performance. If injury didn't affect performance, then we wouldn't really care about that.
That's fair. So we probably have injury and performance. We have a lot of injury and performance data.
Yeah.
Performance data is not in our AMS, but we could go to the records and extract it and match it up. What we don't have is continual training stress type stuff.
So I mean, what I'm thinking of doing, because it's compulsory for the swimming group to have to do it now. It's linked to their funding, so they get their funding docked if they don't do it anymore. So build it in, using them as a subgroup, and once that's shown to be effective with them, I guess, then we can probably expand it to the wider QAS people, and then we can then be a little bit harsher, saying, okay, well, this is the framework for actually getting your data, because it's going to have to make that decision because of this, and this, and it's been shown to do that.
Yep.
Which I think is the main issue we had with AMS in the first place.
Yeah, so at the moment you're using a stick, but you want to create
Eventually,
the carrot.
But if you didn't have that sort of analytics, and you were just sort of collecting data and not making better decisions because of it, why would we be collecting that sort of data? Sort of thing. So,